Good evening.
Good evening, sir.
Good evening, Ramji.
Mm. Sir, is my slide visible?
Yes, Ramji. It
Okay.
is visible. Yeah.
Okay. So I think we can start now. It's already 7:03. So,
Okay.
good evening, everyone. Welcome to the 11th online tutorial session of the NPTEL course, Polymer Reaction Engineering. I'm, um, it's, yeah. I'm Rahul. I'm a Prime Research Fellow from the Department of Physics, IIT Kharagpur. I'm handling this online session for the NPTEL course, and here we'll basically discuss the questions that would be generally useful for your assignments and your examinations. So this is the 11th week, and it is the second last session, official session. And as I told you, sir, as I told you, like on the next week,
Rahulji, you are
Wednesday.
muted.
Okay, I'm muted. Okay, okay. Now am I audible, sir?
Yes, yes,
Yeah,
yes. You are
okay.
audible.
So as I told you, sir, on the next week, Wednesday, we can have a extra session on Wednesday.
Oh, very good.
Okay.
Right.
So
Thank
here
you.
are today I have prepared about 25 questions, and mostly they are multiple choice in nature, and some of them are from the previous year assignment questions. So and made sure that like the questions that I made look similar to the like it is similar to the assignment questions, so it will be much more useful. Okay.
Okay.
So the first question is like particle nucleation may occur through dash and dash nucleation. Yeah. So it is very obvious question. So, basically, it can be homogeneous or heterogeneous.
Unheterogeneous. Yeah.
Yeah, it can be homogeneous or heterogeneous kind of nucleation. So yeah, this is very easy question, but still this time it was related to this kind of nucleation. This question was added, and the next question is Schmidt-Werder class cases 1 and 2 in polymerization is called binary system, 0-1 system, ideal chain system, radical flux theory. Smith what cases 1 and 2 in polymerization is called binary system, 0-1 system, ideal chain model, radical flux theory. Yes, sir?
Is binary like
No, sir, it's like a binary, yeah, but it is generally called as a 0-1 system. Um, it basically depends on the availability of free radicals. If there is a presence of free radical, it is like case 2, so it is called one system. If it is not available, it is case 1.
okay,
So by
okay,
the
okay.
availability of free radical, it is generally classified as it is case 1 and case 2, and it is generally called as 0-1 system. So the particle nucleation will occur due to both the homogeneous and heterogeneous nucleation mechanism if choose the correct option. The monomers is soluble in water. The monomers are water insoluble. The concentration of the surfactant is small enough. So it's actually from spelling mistake. It's small enough for the formation of micelles. The concentration of surfactant is high that the micelle formation can be easily occur. One is small, one is high, one is soluble, one is insoluble.
First option is like monomer should be insoluble in water so that we will get a dispersion and the concentration of micelles should be high. Surfactant should be high to sustain that micelle. The
No,
D option is clear.
no. Actually it is said that the first option should be water soluble.
Water soluble or polymer? Okay, generally
Yeah,
okay.
just we are talking about inoculation. It should be water soluble. It is
Mm,
only then the reactions will takes place, and so the monomers and the second option as is said is correct. It should be high, so the micellar formation is. The options are
okay.
option A
Yeah,
and option B.
I had a doubt about that polymer solubility, like a monomer should be soluble in its own polymer, like that one option. Okay, okay, here it is correct. Particle nucleation, it is correct.
Okay, okay, okay. So what like the question so that Sir was telling was from your assignment question,
No, no, no,
not
not
from the lecture.
yes, from the lecture. I remember that way.
Yeah,
Most of
there
the
was a something. Yeah,
polymer, where
yes,
it
yes.
will be monomer will be soluble within the, or polymer is soluble within the monomer.
Yeah, that we discussed in the last class, right?
Okay,
So I
okay,
remember.
correct.
I don't exactly remember. Yeah, that was the basic characteristics for some.
Okay,
That
okay,
yeah,
clear.
that was from last class. Okay, so let's go to our next question. Yeah, that is high and it is soluble. So the statement is like the advantage of operating emulsion polymerization reactor under limited monomer supply maximizes the production rate and yield. So like the it is saying that the advantages of immersion polymers are it requires limited monomer supply and then it can get you maximum production rate and yield.
One doubt is that with the limited supply of field or monomer,
Yeah.
how it can grow up. But there is one more point also is that emulsion generally we convert once we create the SLA and polymerization forms, then we have to convert it into powder. Like we non-solvent addition will create a powder also.
Mm-hmm. Diversity under limited monomer supply maximize the production rate. So will this limited monomer supply will maximize the production rate?
Yeah, there only I have a doubt because
Yeah,
when we have a limited supply, how
yeah,
it will.
that is a wrong statement, I guess. So it should be that particular part should be wrong. So it is the answer is false. So yeah, the limited monomer supply again question takes the questions here. Question here. Yeah, answer to this statement, this question, so this is a false statement, and I think the major reason comes from this particular limited monomer supply.
Okay, okay.
Okay.
Because presence of higher monomer also there may be an
Yeah,
issue.
yes, but there should be some kind of optimum.
Yeah,
Limited
exactly,
supply,
exactly. Limited is
giving,
very
yeah,
minimal.
yes, giving a limited supply and expecting a higher rate is not true actually. Yeah, there should be an optimum supply of monomers and
Exactly.
that will give you the maximized production rate and yield. Okay, okay then. So the next question is the amount of surfactant that is dissolved in aqueous phase, which is represented as SFW in case of heterogeneous nucleation in emulsion polymerization, can be obtained in terms of total amount of emulsifier in the reactor, which is given as S of T. The unit is mole. Total surface area of polymer, which is represented A of V star, uh, m square, which is the unit is it should be m square, it's meter square, and the parking area A. So we are basically asking for an equation. We are basically asking for the correct equation for the surfactant amount of surfactant that are dissolved.
I
So
think that
which is a,
ABPAS is the option.
yeah.
Yeah, brackets if we say, I think option first is more correct. Anyway, it is minus.
Yeah,
We have to do the minus, but when we see the brackets alignment, if you see, then first one should be the right answer.
yeah. First one is the correct answer. Major difference from this and this is that, yeah, it is like, yeah, your first option is like S of t minus A of p star by A of s.
Exactly.
And
The
the
other one is full bracket
option
of
C
this.
is like, S, I mean, not S of t, yes, I am S of w. This third option is like it is equal to S of t minus A p star divided by A of s. So, so the correct equation is option A. That is the basic difference between option A and option B. Yeah, it is given in such a way that it confuses the student. So yeah, so this is from a previous year history. So yeah, this is the correct option. A is the correct form of the equation for amount of surfactant that are dissolved in the aqueous phase. Okay, okay, fine.
Clear.
Yeah. So the next question is the rate of formation of particles by homogeneous nucleation is the rate at which the oligoradicals growing in the aqueous phase exceed the maximum soluble length.
This is true.
Yes, this is a very true statement. The rate of particle homogenization is the rate at which the oligoradicals growing in the aqueous phase exceeds the maximum soluble length. So it is a true statement. Ah, it's a true statement. The answer is option B. It's a true statement, so let's move on. Linear emulsion polymer can only be formed if the average number of radicals per particle is greater than 0.5.
Here I have a doubt because actually this there is an equation which relates this, but
Yeah,
ratio which should be false.
yeah, it is a false statement. I don't exactly remember what was that particular value, cutoff value. Again, yeah, I remember this is a true statement. I forgot to look for the value, the correct value. Yeah, this is a false statement. Okay, fine. So next question is, in emulsion polymerization, the polymer migration results to the increase in the size of the cluster due to the polymerization in the cluster, diffusion of polymer into the cluster, and coagulation with other clusters. This migration is governed by van der Waals forces. The internal viscosity of the polymers are low, then choose the correct option. Equilibrium morphology cannot be achieved. The polymer form will have larger interfacial and surface tension. The van der Waals force will remain minimum between the particles. The process of polymerization will be on its higher side. This was
Yeah,
discussed while discussing this whole idea
yeah.
of motion.
Actually, yeah, I understand that this van der Waals force is a factor which has to be maximum. I think other than C, all three are correct.
No, actually, it is a one answer. There is no only single option question.
Because I remember in lecture I have seen all.
Yeah. But yeah, okay. I remember. So here, yeah, I again remember. So here, equilibration morphology. Yeah, this one is cannot be here. It is said that it is low. Then equilibration morphology cannot be achieved. The polymer form will have higher surface tension. This is true. The process time from mm, on the higher side. This is a very true statement. And equilibration morphology cannot be achieved. There was two cases. One is for a higher viscosity internal and the other is for the lower viscosity. So I have framed this. This is from a previous year question, but I have framed a similar question. So,
Yeah, I think that is MSQ type.
uh, which one?
No, this is like an MSQ type.
Mm-hmm.
So which means multiple options may be there because
Multiple.
actually I remember that this particular scenario, as you told rightly, there are two options. One is for low
One is for
viscosity,
low and one is for high.
one is for high. Yeah.
Yeah, the prescribed answer according to the for the last assignment was option B. But I, yeah, as I remember, as the viscosity is low, then the van der Waals forces will be minimum. Yes, obviously the van der Waals force is basically depending on the distance of separation. So if the viscosity is high, the viscosity is high, then the density of the particles will be lesser. Hence, the distances can be in the larger side. So then the van der Waals force can be minimum. So that can be a true. Equilibration of the morphology cannot be achieved. Equilibration of morphology, I have a doubt in this one. So let us fix this question. So I have prepared a similar question. So from that we will be able to get a better conclusion. But according to the assignment question that was provided for the last semester or the last run of this course, the answer prescribed answer is option B. I think this one is a true, and the process time of polymerization would be a very high side. Yes, that can also be a true. So so viscosity is like it basically means number densities. So again, yeah, again let's see. So for now, the correct option is option B, and let's see if they have multiple answers correct in this one. Okay, okay, yeah, okay, fine. Two options are correct. This one is also true. Okay, polymerization time. So other two, let's see. As I told you, we'll be going to that similar question, then we'll get an answer. Okay. The difference between continuous stir tank reactors and continuous loop reactors designed for the emulsion polymerization are: CLR reactors have high surface to volume ratio. CLR have high conversion in low residence time. Particle distribution in CLR is easily adjustable. Coarser particles can be easily produced inside CLRs. CLRs require less surfactants.
Here, I think first one is correct. Like CLRs have high surface to volume ratio
Yes.
compared to CSTR, and high conversion also with low residence time. That is the main
Yes.
purpose these two are there. Other
Yes.
three, I am doubtful. I don't think it is
Yeah.
easy to manage the particle
Yes.
size. Proportional also cannot be, and the
Mm.
CLR requires more surfactant.
Yes, it was much effective. So basically, the main advantage if we are talking about this continuous loop is that we can we can adjust the heat conduction, all those things can be very much. So there can be multiple tubes, continuous tubes of different sizes can be arranged. So yeah, the answer to this question is option A and option B. Okay. Suppose you are an engineer and want to produce an emulsion polymer using CTR with uniform particle distribution. What is the correct modification you suggest to achieve this target? Incorporation of tubular reactor before uh, CTSR, incorporating multiple CTSR in parallel, incorporating batch reactor before CTSR, modifying CTSR into continuous flow reactor. So the major thing is uniform particle distribution. The previous one we saw that it is not possible to get uniform particle distribution from the CST. So which kind of reactor would give you uniform particle distribution? That is a basic question. One is tubular, the other one is like parallelly arranging this. One is like using a batch reactor, and the other using a continuous loop reactor.
Is it A, incorporating a tubular reactor?
Yeah, it is a tubular reactor. So tubular reactor would generally give you uniform particle distribution. So the correct option is option A. tubular.
Are there any other options also, like only A or other options?
Yeah, the option is just A. Pulse tubular reactor are better than single pass tubular reactor as they provide improved mixing, less pressure drop, easy cleaning and reinstallation, all of the above.
Main advantage is having improved mixing.
Yes, it improved mixing.
Whereas other pressure drop and other things, all these are difficult.
Mm. Easy cleaning and reinstallation, it is basically we go for like we, yeah, no, it is like installation stuff. Yeah, the answer to this question is option A. Provide improved mixing. Provide improved mixing. So, yeah, this is the answer. So the next question, emulsion polymerization reactor should allow fine-tuning of the polymer microstructure, be useful to prepare many different grades. The same reactor be adaptable to a wide range of production rate, all of the above.
Should be all of the above.
Yeah, all these are the basic characters. So this was taken directly. So this question comes directly from this slide itself. So all these three are the major advantages of emulsion polymerization. So yeah, it allows fine tuning of the polymer microstructure. It can prepare, mm, be useful to prepare many different rates in cell reactor. Be adaptable. It is adaptable to wide range of production rates. So yeah, these are considered as advantages, or it is considered as the minimum qualification to call something as a emulsion polymerization. Okay. The polymer migration result to the increase in the size of the cluster due to polymerization in cluster, diffusion of polymer into the cluster, coagulation with other clusters, or all of them. This is again a very logical question.
Should be diffusion of polymer into the cluster.
I think all of them can be the answer, right? So we have a cluster
Okay, if we
and
count.
some other polymer actually enters, and this can undergo some polymerization and that can lead to some increased size and diffusion of other polymer into diffusion of polymer into polymer. Yeah, I mean this one is for this, and polymerization in the cluster. Again, polymerization within the cluster can increase the size of the cluster, and coagulation with other clusters. So we have multiple clusters, and that they combine together to form a bigger cluster. That is also possible. So I think all of the above can be a correct option. Yeah, the answer to this question is option D, all of the above. The migration is basically governed by two interfacial forces dash and dash.
Diffusion,
Migration of polymers is basically governed by two interfacial forces. What are those two interfacial forces?
surface tension,
Surface tension. Again, if we go a bit deeper, it is surface tension itself. So the basic reason behind the surface tension is van der Waals forces.
Van der Waals force.
okay, okay.
Van der Waals. Uh, again, like van, yeah, van der Waals force of it can be both attraction as well. It can lead to attraction or repulsion, and also the other one is the viscous drag of the migration. Viscous drag. Viscous drag is basically when if you have a fluid, if we have a fluid, viscous drag is like when one layer of the fluid moves and its movement is basically hindered by the due to its viscosity, the whole movement is hindered because of its viscosity itself. It is the viscous drag. So two the major interfacial forces are one is van der Waals forces, another one is viscous drag. Viscous drag. Yeah. The van der Waals forces are dash. the interfacial surface temperature are equal to alphas are equal to the interfacial surface tension less than interfacial surface greater than interfacial surface tension proportional to interfacial surface tension.
Less than.
less than.
It's like it's proportional to. Last also we said like so van der Waals forces is the force of attraction and repulsion. So as the van der Waals surface tension increases, basically says that the particles within the system are well attracted to each other. It's not so that is why it is like forming a it is tending to forming a layer. So the particle attraction between these particles are very good. If the van der Waals forces are less, then these particles will tend to move away, and there is no proper connection between these particles, and hence, and hence that can lead to lesser surface tension. Higher surface tension means higher van der Waals forces. So, like it is proportional to van der Waals forces.
Okay, clear.
So, if it is less than, then there is like there is no connection between these particles, and then there is no point in and then they won't contribute to um, a tension like a surface tension. Okay, okay, it's proportional to. So the internal viscosity of particles are high, then the equilibrium morphology can be achieved. In the in case of particles with low internal viscosity, the metastable morphology will be obtained. So this was the question that I was talking about. What is the answer? Statement 1 is true, statement 2 is true, statement 1 is true, statement 2 is false, statement 1 is false, statement 2 is true, statement 1 is false, statement 2 is false. Again, it is again come back to this how this the higher internal viscosity can it contribute to equilibrium morphology, or is it that low internal viscosity that contribute to equilibrium morphology? Is it possible? Or is just
Viscosity, higher the viscosity, will have a stable system, right?
so
When the particles forms, yeah, when a particles forms, we can make it. But one is that okay? Equilibrium morphology. We are talking about size.
yeah.
But low internal viscosity, generally we have the difficulty of maintaining that shape, all these things. So the morphology control will be better when we are having higher viscosity. That's understanding. Probably we can discuss.
The answer to this question is like it
Both
is
the
a huh?
both the statements are false, I think.
Yeah, both the statements are false. Actually, it is the other way around. So there, as Sir said, there can be multiple choices. Correct. So there, it was again we were talking about low internal viscosity, and the one of the answer is like formation of equilibrium morphology. So that was also true. So here it is actually the other way around. Higher the higher the internal viscosity, then it will form a metastable morphology, and lower the particle size. I mean, lower the internal viscosity, equilibrium morphology can be obtained. So it is like both statements are false. It is the answer is like it is the other way around. High viscosity gives metastable state, metastable morphology. Metastable means it can have multiple stable morphologies, and low viscosity will become equilibrium morphology. Metastable means it can just morphology can just change. Okay, so so there are multiple stable morphologies. Whereas in low viscosity, there will be an equilibrium, just one kind of equilibrium morphology. That is about Okay, so anyway the answer to this question is option B. Both statement 1 and 2 are false.
Clear.
Here, metastable indicating what? Can you explain again?
Metastable, it basically means there are metastable, there are multiple options. Metastable, there are multiple stable. So basically the morphology can vary from one to another, and mostly all are stable in nature. Whereas equilibrium morphology is the one where it will equilibrate to just one kind of a morphology.
Okay.
Emulsion polymers are products by process whose microstructure is determined in the reactor. So, so this is the statement, product by process. So is it a proper definition for emulsion polymers? Product by process means the product is determined by the process by which it is made. So this is a true statement, or the product is made by the process which is involved. So is it a true statement or is it a false statement?
Primarily, that depends upon the ingredients like surfactants or miscellaneous.
Mm.
Reactor means the agitation speed only comes into picture. Higher the agitation speed, that only. But reactor volume also, like shape of the reactor also. One of the lectures it was discussed about the shape of the lecture as well as any agitator speed is there in the prime criteria. Whose microstructure? Microstructure is something different. Particle size we can tell, but the
Yes.
microstructure is something else.
Mm.
So there it depends primarily on the ingredients and the process conditions.
Mm. So basically, this is a definition for emulsion polymers. It's a true statement. That was explained in the lecture also. So it is kind of a basic fundamental statement to emulsion polymers. It is a product by process. Polymers are product by process. Again, this is a term that is generally used in manufacturing like this. So this product by process term. So yeah,
Okay.
answer to this
Here,
question is
product by
it's a,
process.
huh?
Yeah, yeah. The word product by process indicating this polymer is forming in terms of product by some process.
Yeah, the product is dependent on the process. So the process dependent. So if it like the processes involved in the production will alter the products that we obtain. So if we alter the process, we can actually alter the products. So that
Different microstructure will be obtained.
yeah. Mm. So this is a true statement and it is a proper definition for emulsion polymers. Okay. Now, yeah. So emulsion polymers are polymerization reactors should allow fine tuning. Again, this is the same question, but there's a small difference. Allow fine tuning the polymer microstructure, prepare many different grades in same reactor, works in constant product rate. All of the above. So one of yeah. Since we have discussed a similar question, I can give you a hint that one of the options provided here is wrong. Yeah, we have discussed a
Yeah,
similar question.
That
yeah,
is also a wrong.
So
yeah,
yeah, please.
yeah, one and two. I think it is already there clear.
Yeah,
What is on constant product rate only? I have a doubt. But okay, that is also again one problem. What we discussed, a wide range of product rates is possible, but constant product rates only I have a doubt.
yeah. That is the thing.
But
It's not the constant product rate. It is actually a varying product rate.
mm,
Works in varying product rate.
Yes, yes.
yeah, if that is correct, means then all of the above will be an option.
No, that is not correct because it is not constant. Yeah, the statement which is given here is like it works in constant product rate.
Yeah,
But
if it
yeah,
is
so
constant,
this
means
is
that
like
option,
yeah,
Here
that
A
option
is
is
correct.
yeah. As we discussed in the lecture also, like the one of the demerits that we will be facing is like it cannot works in a constant product. basically works in a varying product. So the
Yeah,
answer to
but
this
the
question,
option A and B is okay, no?
yeah, option A and B is okay. So the answer to this question is option A and option B. Okay, okay, fine. So the dash still tank reactor is the most widely used. So which one is the most widely used still tank reactor? So we have discussed many types. One is batch type, semi-continuous CTR. So which one is the most
Continuous
commonly?
still,
Huh?
continuous still track.
No, actually it is semi-continuous. So major reason is because of it has like the it is like major like what we say it is much more flexible to reaction parameters, and that was like mainly quoted in the literature in the lecture. Semi-continuous is the stirred tank reactor is the most widely used one.
Okay.
The dash and dash in the feed in semi-continuous stir tank reactor can be adjusted depending upon the composition and the volume of initial charge, the composition and the flow rate of the feed, temperature, polymer composition, time, volume. So the two properties that can be adjusted depending upon the composition and the volume of initial charge and the compositional flow rate of the feed. Temperature, composition, polymer composition, time, volume. Reaction temperature, reaction polymer composition, reaction time, or reaction volume. What are the two correct options?
Yeah, second one, I think it should be volume because when we talk about flow rate,
No?
can be adjusted with respect because option one and two depends upon the second option says that the composition and flow rate of the feed
Mm.
uh, can be adjusted. Composition and flow rate means there when we adjust the flow rate, then volume of the reaction changes. But composition and volume of the initial charge, first option only.
I can repeat once there.
We are actually depending on the properties within the within the reactor, or the properties within the reactor that can be adjusted flexibility. So the answer to this question is basically
It is semi-continuous.
temperature and polymer. Maybe there is a confusion because there are two options that I myself put. So maybe that's the reason the options is giving you a bit confusion. So So the answer to this question is temperature and polymer composition. So these were the correct options. Yeah.
Just I wanted to ask just to clarify in the feed in semi-continuous stirred tank reactor.
Huh?
When you talk about semi-continuous, so we are not putting at a time all the monomer into the feed tank.
Yeah.
So is it something related to time interval where we will put all the initiator or the monomer
Yeah. I told you like I
all the
made a
time?
bit confusion because I already like I myself put these two questions. So I mustn't have added these two
Even
questions.
even even
Yeah.
even
I think there can be
that
multiple as
view
we if we
also
go.
coming
Mm,
to my mind.
yeah. Again, if we go deep further, like definitely there can be the definitely reaction time can be depending upon the initial charge and field. So I think multiple options are pro can be obtained because since I myself put the other two options, I think that makes the whole question a bit confusing. The recommended answer is temperature and polymer, and it is explained in the lecture. It is from the lecture. So I think these two options are
Just
also kind of possible because anyway, since we are changing the flow rate, then it can impact both time and volume. Definitely, reaction time and volume.
just generally. Just generally, just
हाँ
I wanted to know, in general, I just wanted to know one thing.
हाँ
Suppose in
सर
the
आपका साउंड
semi-continuous
थोड़ा कम है क्या?
sound, now it is coming,
या
sound? Yeah, yeah. I just, in general, I wanted to ask one thing.
ओके
Uh, in semi-continuous stirred tank reactor and continuous tank reactor, in both the cases, what is the difference that make it semi-continuous and continuous?
semi continuous major difference.
Is it in a continuous mode we are putting monomers into the solution, like the aqueous medium, and in the semi-continuous we are putting in a interval of time, uh, based on the missiles or based on the polymerization taking place inside
uh,
the remaining radicals
I think it
or
is.
monomers.
Yeah, yes, it is definitely it is depending on the like continuous basically come from like like the movement of the reactants. So in in continuous it is like it is basically following a continuous. It is like the reactants are continuously supplied to the uh,
Supplied,
yeah,
yes.
reactants are continuously supplied. But in semi-continuous, it's like it is instead of giving it continuously, it is like giving in parts by parts. So,
uh, as there will be during the reaction the temperature evolves,
uh,
and in the lectures I found
uh,
it has been saying it is exothermic reaction, so it leads to fire sometimes get out
yes,
of control.
yeah,
So what I was assuming,
mm-hmm.
suppose if in terms of continuous stirred tank reactor, if
Reactors,
you are suppose continuously giving
yes,
monomers and
definitely.
you are keep on
We'll have a lesser control over
like
those
yeah,
continuous.
yeah, yeah. So in
Yes.
that case, how to like manage the things so that it doesn't get, so is it like definitely in continuous stirred will continuously put all the radicals monomers and all the things into the and continuously stir the things to initiate the uh, polymerization until unless we get the uh, distribution.
Hmm. Yeah, I think yes, that is a very good option. Like if we material is applied continuously, then the chance of controlling if such like when if there is like higher pressure building, so if the gas that if there is any kind of gas evolution is high, so sometime if you need to control some kind of such parameters, then it is will
Mhm.
be much harder to control. So but in
Might be that reason semi-continuous is mostly
yes, my
preferred. I
reason.
think for that
Shravan
reason.
sir, can you give some insight on this since if sir has some.
Yeah.
In our system, most of the products what we use is of
Hmm.
batch reactors because of the process. Because we need to fine tune the polymer for specific requirement. But industrial scale, because we don't put too much this one for what we can say product costing, because our production outputs are fine tuned for a specific product, and the quantities are slightly like what we can say for the requirement. Whereas semi-continuous is what Parthaji said. I also agree with him. Like when we how to have a like one is the control, another one is the output. Both can be achieved with this semi-continuous. Maybe that is the reason they are going with semi-continuous. Continuous, generally we fix everything. Like I want only the product output, and process is fully optimized.
Hmm.
And like regularly means whatever the composition means, composition is not going to change. So
Hmm.
it is a different composition, and I need to get a continuous output without wasting much time. Means I will go for continuous option.
And also, I can like in semi-continuous, the thing is that if we need to have certain time, if the reaction happens, and if some amount of time should be given for that reaction to continue. So if we
Exactly,
give a
exactly. That is
batch
yeah.
of reactants, and they react and they give products, and that takes a bit time. If we supply more number of reactants, and then the reaction whole reaction time may increase, and like oversupplying is also not good, right? So we supply optimum amount of time reactants, then it does the process, get the product, and then we supply the next batch. It's just like the batch reactor.
Yeah,
So
exactly. Yeah, but that depends upon again. I told
again,
like
yeah.
here actually in Reliance I have visited this naphtha cracking plus this polyester production yard, where we start from a gas continuously. They produce and convert it into a polyester fiber, then it converts into yarn and fabric like that. So that is like a continuous process. They know the process is fully optimized. Only thing output is the criteria. So there we go for it. Whereas in pharmaceutical industries and specifically our application, space application, we generally prefer batch reactor only because that quantity is not that much high. Even if it is there, we go for some tailored properties which we cannot achieve through currently through continuous process.
The purity.
So, Savan sir, is it like this? Suppose in a continuous batch reactor, the desired molecular weight distribution polymer we are not obtaining in this process.
No, actually, we can obtain, but only thing is that, for example, if I want a narrow range of molecular weight distribution, and I fine tune the process for that, and definitely continuous polymerization will help to give you a narrow distribution and give a polymeric or output also. Whereas here I am talking about some polymer where I look for a very wide molecular weight distribution. Say I will have a polymer which is having say 1,000 numbers also, like a number average, and it can go up to as high as 1 lakh. So that is specifically tailored to meet the end use requirement. So when such a wide range of polymer distribution is required, I am specifically tailoring that property because after this polymer is going for some other application as a binder. So there I need this much wide distribution so that my final properties of that material, like composite material which I am going to have, will have the advantage. So there I go for batch. So as you rightly pointed out, once we optimize the process for a particular say molecular weight, either it is low or narrow or low or high, whatever it may be, but it should be like a very narrow distribution rather than a wide distribution. Then continuous polymerization is more preferred to have higher yield or more output.
It's a pre-optimized process in terms of like for the case of continuous start.
Yeah, actually,
Like that it is.
like pre-optimized means it should be well optimized. Otherwise, your loss will be very high. Once you don't
Yes,
have
yes, certainly, certainly.
yeah,
So this means that we should have a clear idea on what is happening at every point, and if you are very confident about the whole process,
yeah.
then continuously it can be.
Yeah,
Exactly.
why I'm specifically telling like butadiene, just for to add an example, butadiene, when I have to convert it into polybutadiene, again it's a polybutadiene binder. Like when I do in batch mode, I can have a very precise control of this what we can say initiator concentration, and termination also I can have a control. But when we go for continuous polymerization, you can add initiator monomer along with the polymer. It's in a solution polymerization with the solvent, you go ahead. But termination, when it comes to termination, you have to do that separately. It'll be like as the molecular chain grows up, it ends up by termination by disproportion or coupling. But we have some excess free radical. If I have to kill means in batch, I can terminate at any given point of time by simply quenching that free radical killers. Whereas in continuous, that I cannot do. I have to do at the end only. By the time already this molecular weight would have been crossing the limit, or it will come to that limit, but further it will be like a more of like additional free radicals will be there. I have to take care of the quenching further so that it will not propagate further in the storage.
For this maybe reason, batch mode is mostly preferred.
Yeah, actually, I am telling my experience, but as we see in industries like Reliance, I have seen that plant also in Azira. So there actually end to end like 5 kilometer radius plant from back, you get the gas like Azira port, you get the gas in the barge, and as it crosses through various steps and front side, you see it is converted into fiber, is converted into yarn to fabric, and it is sold as a fabric in Agio. So they have that end-to-end plan, but I understand that it is a continuous process. Nothing is batch there. because they will there they look only for the product output.
All commercials prefer continuous.
Okay. I think we can go to the next question. So yeah, that is a so thank you, sir. Thank you, Shravan, sir. So the basic differences come, as we said, that the basic difference comes from the certainty of the products that we get out of the reaction. If it is very much certain that we get some reaction or product out of this reaction, we can go for this continuous. And if we need to have a greater control over the purity, then we can go for this semi-continuous. Okay.
Semi-continuous.
So well optimized reactions can be done by this continuous process. Okay.
Yeah.
Okay, then. Yeah. So the major limitation of semi-continuous still tank reactor operation mode is comparatively. Yeah, again, this comes back to the discussion that we had. I can introduce it. The answer is low productivity. So that we say like we are dependent, we are controlling more. We are on the here we can have a better purity, as sir said. If we are looking for higher product purity, then the productivity, even though if productivity is lesser, and some cases we go for purity. So semi-continuous
Very
state
certain.
bank has
Yes.
comparatively lesser productivity. So low productivity is the answer here. So semi-continuous state bank reactor allows modification of various unique polymer properties such as copolymer composition, molecular weight distribution, polymer architecture, particle morphology, and particle size distribution. All of the above, none of the above.
All of the above.
Ah, yeah, it is all of
Is
the
it
above.
all of the above?
Yeah, it is. Even though the productivity is lesser, we can have greater control over many properties of polymer like their composition, molecular weight distribution, the architecture, morphology,
Like
and
it is in
particle
our
size.
hand
Yeah,
how
how
we
we
are
are
like
controlling. Yes,
modifying the things, how much time it is taking.
yes,
Like
yes.
where it is on
Yeah,
our hand.
yes, definitely. By limiting the amount of times the reactants actually spend on the
Exactly. Exactly.
reactor, then we can continuously vary all these things. Okay. So this is the answer is all of the above. Yeah. So continuous time reactors, CSTS, have broad dash, and that's why obtaining narrow particle size distribution in CSTR is quite tough. There can be like in the multiple the previous year questions also there can be multiple possible answers, but among this the most prominent or most suitable answer. So we are basically talking about reactions. So,
Viscosity is there.
huh?
Viscosity can be considered.
Yeah, but again, like since they are reactions, mostly every factors will come into play. So even though so the main answer is residence time distribution. So in a continuous time reactor, they have a broad continuous residence time distribution. So reactants are continuously poured and it is taken away from the other side. So the one chance is that the reactors that came will readily go away out of this reactor, and one time it can just shuttle around and it can remain inside the reactor for a much longer time. So we don't have a proper control over that. So that's
So
a
it cannot stay inside. It
yeah.
is cannot stay inside for
Yeah,
much
we
time.
cannot have a control over that. So some kind of fluid is just flowing. Maybe it can be a gas or kind of liquid. It is just flowing and it is continuously flowing. So the particles within the fluid, one chance is like they will just stick around and it is even though it is flowing, it will just collide here and there and it is like kind of staying inside. And sometimes the particles will just go, reactors will go away directly. So So that is the residence. So there is an uneven distribution of the time it is. Some particles will stay there for much longer time, and some particles will just pass through quickly. So answer to this question is Western time distribution. I have a broad Western time distribution, and that's why obtaining narrow particle size distribution in CSTR is quite tough. Since if the time at which they stay vary, then definitely the particle size, the number of particles that can attach together and form this particle size, that will also vary.
Is it broad or narrow?
Huh?
Is it it would be broad residence time distribution, or it would be
Yeah,
narrow
I
residence
was
time
talking about the
distribution?
semi-continuous. Like we are in that case, we are continuous. We are controlling the flow of particles. We supply, say, X amount of reactants. We continue. So it is not a const. Like it is not a continuous flow, right? So it will just flow into the reactor. It will stay there. Then it will go. Then we pour another batch. So it is like batch by batch. It is getting processed. So the number of time a set of reactors that will stay inside the reactor will be a constant, or that can be approximately, it will be for a certain amount. We can say that they stay for a certain amount of time. Suppose suppose we have in the continuous flow, we are continuously just flowing the
Understood.
fluid.
Understood. Understood.
So it can, due to some hindrance in its path or some kind of,
Yeah, yeah. It is.
it can, some particles may just stay here and other may go just uninterruptedly, they will go. So that can cause uneven distribution in the time frame which they are actually spent inside the reactor. So that is the broad residence time distribution RTD. Mm. So basically that refers to variation in the time particles spent inside the reactor. So as the time it vary, then the size also, particle distribution size, that range will also vary. Okay. So commercially, it is not feasible to incorporate large CSTR because of various complexities involved related to grade transition. So true or false statement? Grade transition.
True.
Yes. So answer.
Yeah, and also like it should be true because of this complexity.
Hmm. Yes, it is true. Hmm. So dash reactors provide very large surface to volume ratio as compared to other type of reactors. Batch reactors, continuous stir time reactors, semi-continuous, continuous tubular.
We have our tubular, I believe, because actually the other we had one discussion about that closed
Yes.
system.
Yes. Yeah. So comparing to all other types, the tubular one has the highest surface to volume ratio. Okay. So various types of tubular reactors that are being commercially used are, so there are multiple tubes, uh, tubular reactors. It may be hard to remember all the name, but still can be asked, or some kind of passive following can be asked, so hence I put this question. So the first one is the single pass tube reactors, then the other one is the pulse column reactors, then the other one is Correct Taylor flow reactors, then the Wicker reactor, then the loop reactor. So basically there are 5 kinds of tubular reactors. Okay, so there are 5 different types of tubular reactors that are commercially used: single pass, pulsed column, Taylor, Wicker, loop reactors. Okay. So dash is a specialized reactor design that uses oscillatory flow. So this is the major thing. It uses oscillatory flow to achieve moderate mixing. It's particularly suited for handling high viscosity fluids. Which among this? So this is the major change. The oscillatory flow. There will be kind of a to and fro flow of the reactor. That will give you moderate mixing. So which one will give you such a? So when we have single pass tube reactors, then the pulse column reactors, then Coué-Taylor flow reactors, Wicker reactors, loop reactors. Any idea?
Here I have a doubt, not sure.
Yeah. So the answer is option D. The Wicker reactor. This is a main characteristics of a Wicker reactor. So as the name suggests, the first one single pass tube reactor, as the name suggests, kind of there's a kind of single passes happening. So at that time the reactions should be fast enough. So there's one, the reactors will pass once, and within that the reaction should happen. So and that is a very simple in structure also. So for single pass tube reactor it is basically it is ideal for fast reactors like plug flow reactions. And the pulse column reactions, here we basically induce some kind of pulses for mixing. Okay, so that is the pulse column reactors. And Coué-Taylor flow reactors. Here the like the shear flow is basically controlled. Like the flow is controlled. So for the reaction to happen, the major then comes this Wicker reactor. Here the major property is like this oscillatory flow, and it is useful for high viscosity fluids. And loop reactor can give you, since there are multiple loops associated. So loops of different sizes are there in this loop reactor, and that will helps in better heat dissipation. So and also if since the structure is like this, it's loop, then the uh, like the what we can say, the time it spends, or like the area, not area in the sense like the, yeah, basically it is the time that reactants can spend within the reactor, it increases. And also we can control the tube length in these loop reactors, and by controlling the size or if controlling the radius of the tubes, we can control the flow of the tubes. So basically in loop reactors we can control the heat transfer, we can control the time for which the particles or the reactants are kept within the reactor, and also by tuning the radius of these tubes we can control the flow patterns. So that is it. The answer to this question is Wicker reactor. Okay. So the oscillatory flow, that property is mainly associated with the Wicker reactor.
Is it to and fro, oscillatory flow,
Yeah.
which is coming back to the initial?
Yeah. Like it is like kind of a, it is basically we are talking about tubular thing. So in the tubular thing, the oscillation means the oscillation of the reactants means it should just follow some kind of to and fro motion itself. So dash in a Coué-Taylor flow reactor is a dimensionless number that characterizes the stability of flow. It essentially represents the ratio of centrifugal forces to the viscous forces within the reactor. So there is some kind of a parameter. It is basically a number, just like we have a Reynolds number. So it is kind of a number that is associated with this Coué-Taylor flow reactor, and that basically characterizes the stability of the flow. And it is the ratio of, again the question can be asked in another way. So this particular dimensionless quantity is the ratio of dash and dash. The question can be asked in such a manner also. So basically it is a ratio of centrifugal forces to viscous forces in the reactor.
When we say directly initial force to viscous force, that represents the Reynolds number only directly.
Hmm.
Because Reynolds number also carries the same definition, like initial force to viscous force.
So it is, we are particularly talking it in terms of this QET flow reactor.
Okay. That
So
is
as we
the
told here also, we are basically controlling the shear flow. We are basically controlling some kind of flow. So again, that can be related. Reverse summary is also some related to flow of the fluid itself. So yeah, talk in that sense. But there's a particular number that is defined for this QET Taylor flow reactor. It is called the Taylor number. The value of this Taylor number determines the stability of the flow. Okay. Okay. For today, I have these are the questions that I have prepared. So again, the first, so I think Pathfinder sir has made few initial questions. So let
Yeah,
me
first three questions
first
only.
take.
Just first three
So the
questions.
first question was the particle nucleation may occur through dash and dash nucleation. So
Rahul, shall I take a leave if you
yeah,
don't mind?
yeah, sure, sir.
Yeah. Thank you. Thank you.
Good
Okay,
night, good night, good night, Suman sir.
good night,
Good
sir.
night.
Thank you, Parthaji. Thank you. Thank you, Rahul.
Yeah,
Bye.
thank you,
Good.
sir. So the first question was that the particle nucleation may occur through dash and dash nucleation. So there are basically two kinds of nucleations. One is homogeneous and one is heterogeneous. Okay, so particles
Okay.
that form a like particular kind of ordering will give you homogeneous nucleation, and particles with some kind of non-uniform ordering, or maybe by addition of some, like the composition of the particles differ, all that will give you some heterogeneous nucleation. So basically there are homogeneous and heterogeneous nucleation. The answer is homogeneous and heterogeneous. So Schmidt class cases 1 and 2 in polymerization. There are multiple polymerization events that was discussed. The one was this Schmidt-Ebert cases 1 and 2. So it is called as 0-1 system. It is called as, so it is generally called a 0-1 system because the 0 and 1 represent the presence of free radicals. So if there is a presence of free radicals, and in that case it is called the 0 type system, and if it is present, it is 1, and if it is not present, it's 0. So the Smith-Award cases 1 and 2 is also called the 0-1 system. Yeah. Again, this was the question. The particle nucleation will occur due to both homogeneous and heterogeneous nucleation mechanism if monomers are water soluble, monomers are water insoluble, concentration of surfactant is small enough for the formation of SLDs, the concentration of surfactant is high, that a SLD formation is, or SLD formation can be easily occur. So the answer to this question is it should be water soluble, and the concentration should be high. So these were the initial three questions that we discussed. The rest is the purchasing was, I think, sir was
Yeah,
present
from
for this question.
from fourth, I've catched it from the question
Yeah.
number 4.
Okay. So next week will be our officially like last class. So
Last
we can
last
again have,
last week.
yeah, last week. Yeah, like it was like 11 weeks flight very fast. 11 weeks, like it's like 3 months is
Yeah, it
going
did
so
like
fast. Yeah, I still remember
so fast. Yeah,
preparing for
yeah.
my first lecture. Yeah. Okay. So the next week will be our final one, and after that we can discuss few previous year. Specifically, we can discuss few previous year questions of these 12 weeks. So around we will discuss. So we should, I think we should move a bit quickly because we have to discuss around. So if there are 12 weeks, and there can be around 120 questions. So that will be huge. So we'll have to discuss it faster. So it will be just like a refreshing
Yeah, yeah,
class. Yeah.
yeah.
Okay then. Okay then, sir.
So okay, thank you,
Okay, thank you
thank
so
you,
much, sir.
thank you,
Thank you.
thank you,
Okay.
thank you.